Thank you very much. So I put this talk together because I really wanted to kind of bring some awareness to some of the kind of newer technologies and newer things that are available in the world of cryptography as kind of solutions to non-traditional problems. And so we'll kind of go over what that means here in a minute. But what we'll be talking about is some of these things that are on the screen there. If you've heard of things like format preserving encryption or searchable encryption, these are all things that we're going to cover at a high level because some of them involve a great deal of math. But the idea is just to understand kind of what options are out there in order to kind of see what might be appropriate for use cases that you're working with, as far as with applications that need cryptography but don't fit well into the kind of traditional model. So who am I? So I'm based in Maryland. I'm an advisor for Ubiq Security, and I'm also was the creator of the OWASP Broken Web Apps project, which still I need to kind of pick up and dust off at some point. But sometimes I go to the Northern Virginia or DC or Maryland meetings, and my favorite food, if you're wondering, nachos. And then if you're wondering who Ubiq is, we're actually a partner with OWASP. We have basically a relationship where we do some kind of co-marketing, but also we have some benefits for OWASP members. So Ubiq is a kind of application layer encryption key management, managed key management. So you can get some free pro tier features and some good pricing just using your OWASP email address if you're an OWASP member. So definitely check it out at the URL there. So when you think about encryption generally, what the kind of things that you normally learn in computer science classes or CISSP back in the day when I went through that anyway, was really kind of traditional encryption design where you're kind of taking in some amount of plain text and you just kind of spit out some random looking data. The idea, the use case was there was no way to tell anything about the plain text based on looking at the ciphertext. That was kind of a design feature. And it was also a design feature that it wanted to be non-deterministic, meaning that you can encrypt the same data multiple times and you're going to get different output. And the way that's done generally is through an initialization vector. So if you're familiar with, this is the cipher block chaining mode, where you've got an initialization vector here that's basically being kind of XOR'd in with the plain text as a way of basically kind of bootstrapping the process with random data. And it gives you that kind of non-deterministic nature in order to give resistance to certain types of cryptanalysis. And but it also results in kind of ciphertext that's not ideal for some ways of handling anyway. So it's generally binary data. So even if you start with text, you're going to end up with binary data on the output. It's usually going to be larger than the original plain text because you've got an IV, you've got padding. And if you need to encode that data, so if you've had text originally, it gets turned into binary data, then you need to either hex encode it or base 64 encode it, then that's going to make it even longer. So it's not ideal for most ways of handling. And then the one exception you might have there is sometimes it ends up being smaller if there's compression involved. So sometimes schemes, especially if you're dealing with text, will compress the data before it gets encrypted. And that will result in then the ciphertext being smaller than the plain text, which can also lead to strange problems in some situations. So what we're really going to be looking at is just different ways to kind of break that paradigm. So this is kind of the traditional encryption, and we're going to be looking at non-traditional encryptions. And so we're kind of going to go through different mechanisms as far as kind of the solutions, but also introduce kind of the problems that they solve in a way, sometimes one way or the other. So the first thing that we are going to talk about is format preserving encryption. So the idea of format preserving encryption is that you want to maintain the format and length of your original data. So a very common example for this would be something like a credit card number. So credit card number is going to be 16 digits. And if you want to do format preserving encryption on it, you're going to convert that into another 16-digit number. So, I mean, technically, a block cipher is also a way of doing that because you're translating, bits to bits. But if you're familiar with, computer science, like the counting problem or pigeonhole problem, there needs to be a one-to-one mapping because there's exactly as many ciphertexts as there are plain texts. So, there's that kind of mapping, and it also needs to be reversible. So there needs to be a way that you can, get back to the plain text as well. So how do you do that? Well, as a kind of a conceptual example, let's start with just thinking about digits, and you kind of take each digit on its own. In this case, we're actually using digits, but you could just assign numbers to letters or whatever other kind of values that you might have, and we're just going to do is combine that with a cryptographic pseudo-random number generator. So you can use a lot of FPE and other schemes use AES and things like that underneath the hood in order to provide some of the cryptographic guarantees. And so you can use AES to generate a secure pseudo-random number stream, and then you can just combine that. So in this case, we're just going to take simple arithmetic modulo n in this case, which is 9. So we can say, okay, so for every digit here, you can see we're kind of doing this encryption up and down. So the plain text was 1, our PRNG spit out a 4, and so we add those together, we get 5. 2 plus 9 gives you 1 when you're going modulo 9, and so on and so forth. So the idea here is that you're basically going to get, I should say modulo 10 actually, sorry. So the idea here is that we're getting this, and it's completely reversible. So because addition and subtraction are basically opposites, you're still going to have the same pseudo-random stream coming when you try to do the decryption, and you just have to kind of work up. So it's say, okay, 5 minus 4 equals 1. 1 minus 9 gives you negative, so we would say, okay, 11 minus 9, and that gives us 2. 5 minus 1 is 4, and that's how you can basically regenerate back the stream. So this is a way that you could conceivably do something like format preserving encryption. How it's actually done is a little bit more complicated. There's a couple kind of algorithms that are used. Most commonly, you're going to see FF1 and FF3-1. There are a couple other ones there that are kind of not recommended anymore. And as I mentioned before, these use a block cipher as part of the encryption process. And they also use what's called a tweak, which is, I don't know why they call it a tweak. It's basically like a pepper or a salt, where it's, the same across all the different things that are being encrypted, but it's not something that needs to be protected. It doesn't need to be secret. The tweak can be kind of public. And when you're encrypting this data, what you're going to find is that you're basically converting it from kind of an arbitrary space to the same thing. And I can show a little bit of the details on that on the next slide. There's also there are some security concerns when you have too small of a key space, or a space of possible values, that is. So one of the things they've originally, both of these algorithms and some of the other FF algorithms were thought to be secure with like 100 different values, but in reality, they now recommend a million actually. And so that doesn't mean you need an actual million values. It just means that if you're going to have, in the case of a digit, you have 10 possible values. It just means you would need to have at least 6 digits basically in order to have a million possible values. So it's just the radix, which is the size of the number of values that you have, and then raised to the power of the minimum length. One thing to be concerned about if you are looking at this area is that FF1 has some patent claims on it. I don't know if those have really been adjudicated as far as if they're legit or not, but there's at least some people that claim to have patents on that. FF3-1 does not, so that's generally kind of where people steer towards. And if you're working in Asia or South Korea specifically, they've actually got a couple other algorithms that they recommend, FEA1 and FEA2, which I won't get into the details there. But it is one of those areas where you do sometimes have to deal with kind of different regional requirements for storing data. So the reality of how these things work is they're what's called a Feistel cipher. I'm not sure if you guys are familiar with that concept, but it's the same type of cipher that's AES and DES and things like that are as well. The gist of it is that it's some number of rounds that kind of basically are repeated, and what happens is that in each round it takes kind of half of the plaintext data and does some sort of transform on it, and then XORs in the other half of the data that's there. And so this is the reason why something like AES is a Feistel cipher, and it uses 128-bit block length, and that was because when they were kind of designing the putting out the request for proposals back way back when, they were kind of forward thinking and saying, okay, 64-bit processors are going to come, and the characteristics of Feistel ciphers are such that they're guaranteed to be reversible. So the actual transform on the first half does not need to be reversible in order for the whole thing to be reversible. So it's actually, very good for building crypto systems. That's why so many of them, including this, use it. And so AES, they said, okay, we're going to have 64-bit processors, so therefore each half will be 64 bits. That's why they chose a 128-bit block length. And that's why you're going to have the same block size regardless even of what your key size is. So as you go through, you're basically XORing the different sides, and it goes through some number of rounds. The number of rounds varies. For FF1, it's 8 rounds, I believe. FF3-1 is 10 rounds. They also split the input slightly differently. So that's why there's kind of these differences between the two algorithms. But the general concept is the same. And then the general concept also is that, you can basically work backwards. So this left-hand column is your encryption, where you're basically taking the plain text and turning it into ciphertext, and your right hand is the opposite. So you start out with round 0 and back up here to get to the plain text. So that's the gist of how those things work. But the importance is not so much the details of the algorithms, but more just the concepts that these things exist, and it's an option. So in the past, I think a lot of people, when they looked at credit card numbers, they always thought about we need to tokenize it, and we need to build some sort of map that we remember kind of what the original value was and what the tokenized value was. And these types of format-preserving encryption allow you to not have to do that. So you can basically never have to store the unencrypted value. You're able to basically just store the encrypted value and the key just like you would with any other ciphertext. Okay, so next thing we're going to talk about is deterministic encryption. So what this means is basically that you're going to get the same ciphertext as long as you provide the same plain text and the key. And so what this does is it breaks what we talked about before with the initialization vector. There's intentionally no randomization here. You can't. Sometimes there'll be like a fixed initialization vector for reasons, but the idea is that it's not randomized. So that way, every time you run the encryption, you're going to get the same result. And so it kind of breaks that, Boromir's advice here, where it's like, well, no, we actually do encrypt the same message, multiple messages with the same key, because it actually kind of gives you properties that are useful in some cases. So, well, what are those properties? Why would you want to do this? Well, it's primarily in databases. So MongoDB calls this client-side field-level encryption. Other databases call it something similar. But the basic idea is that you're providing it a way that you can say, okay, we're going to encrypt this data, but we want it stored in such a way that we can still run at least a little bit of querying against it. So, you could deterministically encrypt a social security number, for example. And because every time you encrypt the social security number, you're going to get the same ciphertext, then that can then be used as a primary key and even used to join across tables and things like that. It gives you a lot of characteristics that you don't get with traditionally encrypted data. So the idea there is you're basically just encrypting the data before you search. So the database is really not even so much aware that what's happening, because it's all it's doing is getting some data. It treats it as a primary key. The actual kind of encryption and decryption is all happening on the client side. So it only allows direct equality or kind of joins and those kind of queries, but it does allow you some level of being able to secure things in a way that's not going to be just completely using the plain text data. So it's a way that you can kind of compromise sometimes between, okay, we've got social security number, which is a very good identifier to use for people in general kind of HR or healthcare, whatever kind of systems, but you don't want to store that in an unencrypted form. So we kind of treat that encrypted SSN as the kind of primary key across various tables and whatnot. So the problem is there's low entropy, it's susceptible to cryptanalysis. I imagine a lot of people have probably seen this picture before, which is basically using ECB, electronic code book encryption on a picture that you can tell is the Linux Penguin. The idea is that that's a deterministic protocol. So every section of these things that was just a block of white pixels gets encrypted to the same value. All the black pixels get encrypted to the same value, and that's why you can kind of see the outline and whatnot. So that's a great illustration of that. It's also very problematic in low entropy fields. So when you've got something like age or blood type, gender, age again, country, eye color, there's a lot of things that basically there's only going to be so many values that it can be, and then you can start drawing inferences just by the fact that a certain frequency analysis across things. So age, for example, you can compare age in some encrypted data with our chart here that shows the U.S. population by age, and get a pretty good idea maybe of at least what are the older people, because they're in the smaller cohorts, and the more people that are more middle-aged and whatnot. Depending on the demographics of your application or whatever's being analyzed, that may also affect things. So if you're looking at TikTok, for example, the age would definitely skew towards younger, and that would allow you to probably make some pretty good inferences there. And especially if you've got multiple fields that are encrypted in this way, then it can really cause you problems, because then you can start correlating things like, okay, the country that someone is in and their eye color, that in certain countries, certain eye colors are more common, and that'll allow you to basically you can kind of think of it as like one of those kind of logic puzzles of like, okay, eventually you can kind of figure out everything as far as kind of who's what. But that's assuming someone has access, full access to your database to do arbitrary queries and whatnot. So it's ultimately what you want to protect against. But if the alternative is I'm going to have to store all this data unencrypted, then you're certainly improving your security. And there's some other techniques we'll get to later that can improve on this a little bit, but they have issues as well. So all of these solutions and the problems that they solve, it's about compromise. It's like understanding that we're kind of relaxing some of the security constraints on these crypto systems in order to give us more flexibility in what we want to do. So another item that's of interest is what's called searchable encryption. So, we talked in the last one how deterministic encryption allows you to gather, to do searches on equality. So this is a bit similar, but it's not quite the same. The problem space here is more along the lines of, documents. So we've got a collection of documents, maybe that have some sensitive information in it, and you want to be able to search for keywords across those documents, but you don't want to be storing any of that in plain text. So what we want to do then is, before we encrypt the document, we're going to extract a list of keywords, and then we're going to then encrypt each of those keywords along with a reference to the document, and that all gets pushed to the database along with the actual encrypted document. And that gives us the ability then to later query on those encrypted keywords and pull back the document. So the keywords are going to be deterministically encrypted in this case because they need to be able to match up, but the documents don't necessarily need to be. So you can have variable keys on that. So it's really kind of separating out the encryption of the kind of bulk data, like the entire document, from the keywords that are used for the querying and searching. So again, the client is the only one that has the keys to any of this stuff. So the database server is basically just storing all this data in an encrypted form. And what you do run into, again, is kind of frequency analysis. So, there's going to be some common words that, if you're, it depends on how you're extracting keywords, you might ignore some of the very common words, but, things like your name of your company and other things, related to your business are probably going to be very common and, be kind of able to be identified as someone who's able to kind of dump all of the keywords and figure out, this is kind of the occurrences of them across different documents. So that's one part of the problem. But again, you're making trade-offs here. The other kind of thing to think about is kind of the low frequency thing. So if you've got, a very kind of innovative solution to something you're patenting, something like that, maybe a merger and acquisition that's, kind of out of the norm, I guess, for your normal day-to-day operations, then that may have kind of more unique keywords. And so that may symbolize to somebody who's looking at it that this is an interesting document because it has a lot of, unique keywords or keywords that are not seen in other documents. Now, granted, they still can't decrypt the document, so it's you can argue how useful that is, but it's at least maybe, gives them some information. Again, kind of making that trade-off. So one way you can address that, and I had a couple slides here to go into more detail, but I decided to kind of keep this at high level, which is that you can actually make this a little better by maintaining an index of basically how many times you've seen each keyword. So rather than hashing it to the same thing every time, you're going to have a unique hash every time you see the keyword, which then requires that you're going to do some work, when you insert to know how many, what index you should be at for each of the keywords. But it does work out where you can have this that you don't necessarily have this frequency analysis. So if you want to see a lot more detail on that, there's a presentation here from the Chaos Computer Club that goes into more detail about kind of how this works. But the basic idea is that you've got a incrementation there that's going to basically keep it from being the repeatable encryption. And this is also one of those situations where, as far as I know, there's no commercial kind of solutions that currently implement this. So if you wanted to do a scenario like this, you're going to have to basically do it yourself. Whereas I mentioned earlier, for like just deterministic encryption for a single field, like that's something that most databases support already. Okay, so another thing you might have heard of before is what's called homomorphic encryption. And it's kind of a strange animal as far as I'm not quite sure how it got the name. I think it has to do with more some of the mathematical properties. But the basic idea is that it's generally, when you think about homomorphic encryption, you're thinking about like integers or some sort of numbers. And what you can do is you can take the encrypted data and you can perform operations on it in such a way that the resulting kind of ciphertext is going to be the equivalent of performing those operations before the encryption. So the simple example here was as addition. So you've got A and B that you might want to encrypt, and so A and B that you want to add together. So one way you could do that is you could take A and you could take B, add them together, and then encrypt them. But the other way you can do it in this case is you could take A and encrypt it, put it in the database. Later, at some later time, take B and encrypt it, send that to the database. The database then adds the two together, and it's guaranteed to be the same as if you had added them before you sent them or through the encryption process. So I've got an example here on the next slide that'll kind of go into a little bit of how this can work. It generally is, there's going to be some limitations on it, some significant limitations that we'll talk about in a few slides. But it's practical there. It's commonly done with things like RSA, where you've got exponentiation happening. So if you're doing modular exponentiation, you can then do multiplication across that in such a way that you can guarantee that the properties that we're talking about here. So you could also think about string manipulation as being kind of homomorphic encryption. So if you had an encryption scheme where you like encrypted every single character separately, then you could certainly do concatenation of two strings together because you're basically just putting them together in that way. So, but generally when you're talking about homomorphic, you're talking about addition and multiplication as the primary operations. And even though division is technically multiplication, generally these things are working on integers. So doing like integer division is not simple in these cases. So you might be able to in some cases. There's also some cases where you can actually do homomorphic encryption for real numbers, for fractions or decimal numbers, I should say. But what ends up happening is that it's basically an approximation. So what you end up with is that if the encrypted value is not exactly the same as the A times encrypt A times encrypt B is not exactly the same as encrypt A times B, but it's close enough by some delta that's practical for some purposes anyway. So let's just go through a little bit of an example on this one. So so just kind of going down the column here. So let's say we've got a plain text of 3 and we've got a key of 12, and we're just going to use a very simple kind of example cipher scheme where it's like we're just going to multiply the plain text times the key. So we see here that the ciphertext now is 36. 3 times 12 is 36. Now we want to add 5 to that. So because the 36 was already stored on the server, we need to take the 5 and multiply it by 12. 5 times 12 is 60. That gives us 60 that would then get sent to the server and added to our 36 previously. So that gives us a total of 96. So the encrypted data after the second piece was sent would be 96. You can then say, okay, well, 96 is going to later then get sent back to the client, which then knows the key and can decrypt the data. So 96 divided by 12 is 8. And lo and behold, that's 3 plus 5 is 8. So this is basically showing kind of how this can work in a very simple case. And I kind of walk through here a couple more larger numbers where it still kind of works out. What you will notice is that this is all done kind of with standard unsigned integers and stuff. If you want to do things, so what ends up happening is as you multiply two 8-bit numbers together, you're going to end up with 16 bits of possible numbers that you could end up with, and so it kind of expands and contracts the number of data bits that you can have. And you can look at the red item here on the right, where we actually end up using the 9 bits. So it goes above 255 when you add 196 and 104 together. So that's one thing you need to be aware of if you are going to use this kind of homomorphic encryption is just the range of the data in order to make sure that you've got enough room for it and you don't have overflows. Okay, so another example of this that I found really helpful was from this blog post that I linked here. And the idea here is okay, so how could you actually use this in practicality? And so think of it as Bob has a table of stock prices and Alice wants to query and say, okay, I want to know the price of a particular stock, but I don't want Bob to know which stock it is that I'm querying. So it seems like kind of a unsolvable problem, at least not without just pulling down all of the data. So the presumption is Alice and Bob both have plenty of CPU speed, but maybe not so much bandwidth. So we don't want to pull down the price of every single stock. But what can happen is that Alice can send an array basically of encrypted values and say, okay, we're gonna, there's five possible stocks in this case. So we're gonna say, okay, we want to know the middle one. So stocks A, B, C, D, E. So what she's gonna send is A and B are gonna be zeros because we don't care about those. C is 1 and D and E are zeros. And this basically gets encrypted and sent over to Bob. Bob then says, okay, so I've got this data. Bob doesn't know that this is what's happening, but this is what's happening, within the encrypted homomorphic encryption system, that, 0 is multiplied by the stock price for stock A, for stock B, so forth. And so what you'll see then is that you end up with zeros here because 0 times anything is going to be 0, but you end up with the one stock price for the C stock that she was interested in. You can then add all those together, and it just comes out to what the C price was because the other ones are 0. But again, that's just going to be an encrypted result that then is going to get sent back to Alice. So I thought it was a really interesting kind of illustration of exactly how you can use homomorphic encryption in a somewhat practical way. Again, this is something that you would have to implement yourself. I'm not aware of any kind of commercial products that implement anything like this, and that's for with one exception, I suppose. So Microsoft Seal does support some use cases, but it's still kind of a research project. I don't know that a lot's been done on it in the last few years, so I don't know if I would put a lot of faith in it as far as an actual production commercial product or anything. And kind of the holy grail for homomorphic encryption is what they call fully homomorphic encryption, which would allow basically an infinite number of additions and multiplications to happen on the data set. But It's not really practical yet. There's a couple systems I think that have been close to that as far as like they are research projects that have kind of been proved to be fully homomorphic, but the problem is that they're entirely impractical. So one of the examples was, one of them was like, I think one of the IBM systems that they were working on was about 1 million times slower. So something that would take like 1 second on plain text data would take, I think years basically on the ciphertext. So it's just the factors, even though computers are fast, it still becomes a significant problem. So there's really no practical use of this, but it's an interesting concept to be aware of. And sometimes that's also helpful too, because sometimes you get developers that hear about something like this, like, oh, we're going to implement this, homomorphic encryption scheme. And I think that definitely is an indicator that you need to take take a pretty good look at what it is that they are building in order to make sure that it's actually, practical and that it's going to actually meet the security needs of what you have. So the last section we have here is what's called queryable encryption. And so this sounds like magic, and it kind of is a little bit, at least for right now. So queryable encryption is something that really is only implemented right now by MongoDB. So they really, they bought another company that kind of specialized in some of the building blocks that were needed for this queryable encryption. And so they basically set this up so that you can encrypt data on the client side, and then it gets sent to the server side. One of the interesting things, they keep calling it fully randomized. I don't really like that wording, but the gist of it is it's non-deterministic. So you're sending data up to the server. It's not deterministic encryption, but you can still run queries on the data. And right now they just support equality, which is pretty limiting. But they are going to basically support range and prefix and suffix and substring searches in future releases. So that's a very unique capability that no other crypto system has as far as being able to do those kind of operations on fully encrypted data. So the gist of kind of how that works is that again, all the encryption is happening on the client side. So, and this MongoDB driver can interface with kind of standard KMSs as well. So it doesn't necessarily need to be, entirely their key material that's being used. But the idea is that the client side is the only thing that has the keys, both for decrypting the data, but also for encrypting data to be sent up for searches. So it's, the general picture is very similar to what you would get for, typical field level encryption, where, the data is encrypted before it's sent. But what's kind of the magic here is how the data is kind of indexed. And there's when documents are basically added into the store, they're added, there's an index that's created to basically where the data that can be used for the queries. And then also the fact that it is a non-deterministic encryption. So you can see here that it's searching for, 7HU blah, blah, blah. And the record that it found that matched is, D76B. So there's some magic there that's happening as far as kind of how it's able to match those, even though they're not the exact same value. It knows that that's where the data is that the client is searching for. So what they have underneath the hood there is what they call structured encryption. So it's a little strange. Structured encryption is a more of a general concept, but it's really the key innovation as far as what allows them to do this searching here in such a way that they can actually find the data they're looking for. And I think I talked about a lot of this other stuff here. One of the things is that you do need to specify when you create the collection, which fields are going to be encrypted, but also what query operations you're going to allow. So as I mentioned, kind of the magic here is that it's creating indexes in the back end that are encrypted that allow you to do the searches on data. And so if you're just going to be doing like equality searches, then the indexes are simpler than the indexes that would be required to support something like range searches in this case of integers, or prefix, suffix kind of things for strings. So it's very dynamic, but it's also can be resource intensive as well. And then the other big thing with this is, its implementation details are subject to change. So I tried to look to see if I could find some more details on exactly how this encryption works and how they are planning to do some of this other stuff. But because they've only implemented the equality searches so far, and they're still planning to make changes to some things before they go into the allow other types of queries. The alternative was I was going to have to kind of reverse engineer their client to see what was going on, but because the details are subject to change, I think it's best to kind of gloss over those for now. But the gist of it is that you need to make all these kind of decisions up front, so it's really most appropriate for new deployments. If you've got something that's already using like field level encryption, then there's not going to be an easy way to migrate that to this because it requires a different set of indexing and stuff. It really is kind of, you could pull the data over, but it would be basically creating a new database. So in reality, this is not quite ready for prime time. It's, it's in public preview, but they have said that you should not be using it in production. There will be breaking changes. They've, because they just, have additional work to do, I think. And like I said, it only supports equality matches right now, so it's not that much more useful than what you already have available with MongoDB or many other different database servers. And the storage requirements are significant. So the 5 times number I've seen in some places somewhere less, and I think that has to do with, as I mentioned before, what type of querying you're going to support. So the more types of querying you allow, and I think also the larger the kind of data set is, it's going to basically increase the size of your data store. And inserts are also significantly slower because basically every time you're inserting a new record into your database, you've got to then update all the indexes that for that field or that set of fields maybe that record is for, or that the encrypted fields that record has. So it's can be a significant performance impact there when you start getting to kind of non-trivial workloads. So I think it's very interesting as kind of a research thing and something that I definitely want to keep an eye on in the future, but definitely not something you want to start building any production systems on today. So that's it for me. So I've got a few minutes here. Happy to take questions, and just throw the information up there again as well. If you want to take a look at our the offerings that we have for OWASP from UBIC. And thank you guys very much.
Thank you. Any questions?
So on your slide 23, maybe that helps you to, but it says Alice, but doesn't Alice trust Bob here for the, homomorphic encryption process itself is secure? This would only work if this was, third party somewhere else that guarantees that this works, right? Am I missing something here?
Well, yeah. I mean, so you have to trust Bob to, actually send you the data, I guess, that would kind of come through this process. But the idea is that Bob doesn't get any of the unencrypted data. So it's Bob is just going to be receiving the encrypted version of the 00100 and apply that to the data that he has that may or may not be encrypted already.
Yes, so that works. But if Bob is in control of that environment as well, then he could potentially see the data. No?
Well, he would see the stock prices, but what he wouldn't see is which stock price that Alice was interested in. So you think of Alice as a private equity person or something that might want to buy a whole bunch of some stock. So it's a way to kind of avoid kind of an information leak.
Okay, and then the next one is this on MongoDB queryable. I know you mentioned that there's this research from Microsoft that isn't 100% there or at all, but they have something called safe computing environment. Is that an alternative to that? Because you can have data there and then query it from the outside without actually seeing the data or something like that. Is that similar or not? Or not?
Yeah,
thanks, by the way.
I think that's a different kind of technology around basically kind of secure enclaves, as far as kind of how you can process data. And there's other things that some of those cloud vendors and that offer around they call it like obfuscated RAM and things like that as well. I didn't get into those here. I was thinking more at the application layer, but yeah, there's definitely kind of other options out there that give you kind of different levels of security. The concern that I have with some of those things is like, if it depends on your threat model. So I kind of view some of it like, S3 bucket encryption, for example. Like, it's useful for like protecting you against somebody like stealing a disk out of Amazon's data center, but it's not so useful in production because usually the thing is running and the data is, accessible by authorized people. So, I think there's sometimes some of that stuff is more good for checkboxes, I guess, and just be able to say that data is encrypted, but not really being practical, I guess, as far as actually preventing the types of threats that you should probably be concerned about. No problem.
Anyone else? 3, 2, 1. That's it. Thank you very much. It was a really nice talk, and this is it. Our last talk of the day.
Yep. Yeah. Thank you guys very much.